My name's pronounced as Jidong Xiao, and I'm a PhD student from College of William Mary. And this work is collaborated with Lu from VMware and Huang from IBM Research, and my advisor, Haining Wang, who recently moved to University of Delaware. The title of this project is Hyperprobe towards virtual machine extrospection. So today's talk includes 5 parts. The first is the problem statement, including the motivation and the background, and then the design and the implementation of the Hyperprobe framework, and then I'll give some case studies, and finally is the evaluation, and then it's the conclusion. So first of all, what is the virtual machine extrospection? Before we talk about virtual machine extrospection, I want to talk about one term called virtual machine introspection, which is, I think, is a well-known term in computer security community. Virtual machine introspection is a security technique that is used to, at the hypervisor level, one can inspect the virtual machine state, because the hypervisor is in a more privileged level. So in the hypervisor, you can see everything of the virtual machine. So there's a technique called virtual machine introspection, and this technique has been widely used by the security community. But in this project, we are talking about a different term. We call it virtual machine extrospection, which we define it as a procedure to retrieve the hypervisor information from within the virtual machine. So it's a reverse information retrieval problem. And the motivation of virtual machine extrospection are twofold. On the one hand, attackers who is in control of a virtual machine may want to know more about the hypervisor information. And on the other hand, normal users, like those benign users in cloud environment, benign users may also be curious about the hypervisor information, like what software they are using. Are they using the secure kernel or something? So the motivation are from two aspects, both from the attackers and from normal users. They want to know more about the hypervisor. And the contribution of our work is, first we created the term virtual machine extrospection, and we defined it as a procedure to retrieve hypervisor information from within a virtual machine. As the first step towards virtual machine extrospection, we study a specific problem, which is to detect or infer the hypervisor kernel version. And we study the problem in a Linux KVM-based virtual machine environment. Which also we present the design and implementation of a framework called Hyperprobe, which can help users in a cloud environment to automatically detect the hypervisor kernel version. We also evaluated the framework in 5 real-world cloud environment as well as in our own controlled testing environment, and all of which get promising results. So first of all, I will describe some background information. Since our study was performed in a KVM-based environment, KVM is a kernel-based virtual machine, and it's an open source project, and it's also a popular hypervisor. KVM has been merged into Linux mainline kernel since kernel version 2.6.20, and it has been now widely used by researchers and cloud vendors. So at the beginning of our study, we studied the evolution of KVM, which, as I said, has been merged into Linux kernel version 2.6.20 since 2007. And over the 7 years of this study, which is 2007 until 2014, about 3,400 KVM patches has been released by Linux kernel. And most of these patches are either new features or bug fixes. And the challenge of this project is because ideally hypervisors should be invisible to virtual machines. Virtual machines are not supposed to see hypervisors. So retrieving hypervisor information from virtual machines are really hard and has not been has been comprehensively studied before. So in this project, by analyzing KVM patches, we observed that some features, some hypervisor features and some hypervisor bugs can be detected from within the virtual machine. So this figure shows the design or the principle of the Hyperprobe framework. Basically, we use the features and this bug fix to detect the hypervisor kernel version. In this figure, it shows that we use the features as the lower bound and use bug fix as the upper bound. For example, as we can see in the figure, assume feature A is introduced in kernel version 2.6.30, and bug B is fixed in kernel version 2.6.35. If we can detect that both feature A and bug B are existing in the hypervisor, then we can claim that the underlying hypervisor kernel version is in between 2.6.30 and 2.6.34, because only if the hypervisor kernel version is in between these kernel versions, we can detect that both feature A and bug B. As to the implementation, the framework is implemented in C programming language. So far, we selected 19 test cases for feature detection and 20 test cases for bug detection. The detection covers all the 35 major kernel versions between 2.6.20, which is the first kernel version that introduced KVM, and 3.14, which was the latest kernel version at the time of the study. So this table shows the features we have selected. Some features are more complicated, but some features more straightforward and simple. For example, the SMP support, which means that the guest virtual machine can run multiple processors. So the detection is also very straightforward for this feature. As long as we can detect that the guest OS can run multiple processors, we can claim that the underlying conversion is greater than or equal to 2.6.23. And this table shows the bugs that we have selected. One interesting thing is that we can see that there are a lot of bugs MSR related. MSR refers to model-specific registers. The reason that there are so many bugs related about the MSR is that MSR is a model-specific registers. CPU vendors like Intel and AMD defines hundreds of MSRs, and these registers may only exist in some specific process models and may not exist in other process models. So it's very hard for hypervisor to correctly emulate all the behaviors of these MSRs. Therefore, we can say a lot of bugs are caused by MSRs. So next, I'm going to show two case studies, one about the feature detection, one is about the bug detection. As to the feature detection, I'm talking about the KSM detection. KSM refers to kernel same page merging. It is a mechanism to save memory, or sometimes we call it memory deduplication or memory sharing. It is currently implemented in different hypervisors like KVM, Zang, and VMware. For Linux kernel, it has been introduced since Linux kernel 2.6.32. So if we can detect that the KSM is enabled in hypervisor, we can claim that the hypervisor OS conversion is greater than or equal to 2.6.32. So this figure shows how KSM is working. Basically, the KSM is a kernel module inside the Linux kernel, so it will scan all the memory pages. And for each pair of the memory pages, if these memory pages are identical, then KSM will try to merge these pages. and the merged page will then be marked as a shared page. And later, if a write operation occurs at the shared page, then a technique called copy on write will be used. So the shared page will be copied out, and the write operation will occur on the copied page, which is the private page now. But from this procedure, we can see that a write operation to a shared page incurs more time than a write operation to a non-shared page, because for the shared page, there's one more operation, which is a copy on write. So there's copy and write. Therefore, the time will be consumed more than a write operation to a normal page. And based on this timing difference, we can detect KSM. And here's the procedure. In the first step, we load one specific file or some random file into the memory, and then we try to write to each of the pages. And we record the write access time and use T1 to denote the write access time. And then we load the same file to separate the location of the memory and wait for some time so that KSM, if it's enabled, KSM has a time to scan the memory and merge these pages, because these pages are from the same file, just two different copies. So they should be merged because they are identical. And then we record the writing access time to each of the pages, and we use T2 to denote the writing access time. And as I said, a write operation to a shared page incurs more access time than a write operation to a normal page. Therefore, if KSM is enabled, T2 should be clearly larger than T1. So in this way, we can detect KSM as shown in this evaluation figure. The top figure is when KSM is enabled, and the bottom figure is when KSM is not enabled in hypervisor. So we can see when KSM is enabled, T2 is significantly larger than T1, and we can see the significant difference. Therefore, we can detect KSM. And then a case study for bug detection. As I said, there are a lot of MSR-related bugs because CPU defines hundreds of MSRs. And many of them may only exist in some specific processor models and may not exist in other processor models. So due to the large variety of MSRs, modern hypervisors always have trouble to dealing with these MSRs. And for this specific case study, we will talk about IA32 microcode revision. This is an Intel-defined MSR that Intel defines a capability that enables the microcode to be updated in its P4, Intel Xeon, and P6 family processors. So the microcode, if the microcode has some critical bugs, the CPU vendors like Intel will release new microcode so the microcode can be updated. Once the microcode is updated, its revision number will also be updated. So BIOS or operating system can extract the revision number by simply read these registers. And in previous Linux kernel, when the guest OS tries to read this register, KVM will return an invalid value, which is 0. And this invalid value somehow causes Microsoft Windows 2008 to crash. And to fix this problem is also very straightforward. Since Linux kernel 3.2, KVM would return a non-zero value. So when the guest, either the BIOS or the operating system tries to read that register, it will now get a non-zero value. So the detection is also very straightforward. We can simply try to read that register. If it returns 0, then the bug still exists. If it nonces, the bug may not exist. And next, I will show our evaluation results in some real-world cloud and in our own controlled test environment. This table shows the results in 5 real-world cloud, including some famous cloud like Google Cloud and HP Cloud, or some less famous cloud like CloudSigma and Joyent Cloud. We can see from the results that one major observation is that at the time of the study, the latest kernel version is 3.14, but we can see that none of the cloud vendors are using the latest kernels. This is understandable because the latest kernels may not have been extensively tested, so it may have new bugs or may not be stable. So we can see that cloud vendors prefer to use some old kernels. In particular, we can see that Google is using a kernel between 3.2 to 3.3, and Joyent Cloud is using an even older kernel. But as I said, this information are actually private information. Cloud vendors may not release this information into public, so we don't know the ground truth. The only way we can verify it is from some either side channels like these public forums, or we need to contact some person inside Google or some other cloud. So on the other hand, we can verify the results in our own controlled test environment. And this result shows that our results are in our own controlled test environment. In particular, we found 11 exact match for all the certified conversions. And for 15 of them, we can narrow down to 2 versions. And the worst case is only one case in which we can narrow down to 5 versions. Finally, is the conclusion of this talk. We investigated a reversed information retrieval problem in a virtualized environment. And we created the term virtual machine extrospection, which refers to a reverse information retrieval problem. Or in other words, we try to retrieve the hypervisor information from within a virtual machine. And as a first step towards virtual machine extrospection, we started a particular problem, which is to detect the hypervisor kernel version from within the virtual machine. And we present the design implementation of a framework called Hyperprobe. And we got promising results in 5 real-world cloud as well as in our own controlled test environment. So that's all. Thank you.
Hey, check. You mentioned that you used features as a lower bound and bugs as an upper bound when you were detecting. Is there a reason for that?
Because if the feature is existing, then the kernel version must be greater than or equal to that kernel version which the feature was introduced. But on the other hand, if the bug is existing, then we can claim that the underlying kernel version is lower than a version that the bug is fixed. So we use the feature and bug as the lower bound and upper bound.
Any more questions? Okay, thank you.
Thank you.